Hi future engineer, today we will talk about thermodynamic cycles. There are 6 cycles to be discussed in total, and they are as follows: Carnot cycle, Otto cycle, Diesel cycle, Dual cycle, Stirling cycle, and Ericsson cycle. But for today's video, the discussion is all about diesel cycle. So don't be lazy and grab your scientific calculator. So if you're ready, let's begin. Let me introduce you Rudolf Diesel, or in full, Rudolf Christian Karl Diesel. He is a German thermal engineer who invented the internal combustion engine that bears his name. He was also a distinguished connoisseur of the arts, a linguist, and a social theorist. About 1890, in which year he moved to a new post with the Lindt firm in Berlin, he conceived the idea for the diesel engine. He obtained a German development patent in 1892 entitled Theory and Construction of a Rational Heat Motor. Did you know that diesel engines are more efficient than gasoline engines? A gas engine is only about 20% efficient. That means only 20% of the fuel actually moves the car, and the rest is lost to friction, noise, or engine functions, or it goes out as heat in the exhaust. But diesel engines can reach 40% efficiency and higher. That's why they are so popular for moving heavy vehicles like trucks, where extra fuel really starts to get expensive. Diesel cycle is an idealized air standard cycle for compressed ignition engine. This cycle is sometimes referred to as constant pressure combustion. Let's take a look at the PV and TS diagram so we can understand how the diesel cycle works. At process 1 to 2 is reversible adiabatic or isentropic compression, in which the intake air is compressed, leading to a higher temperature and pressure by moving the piston from the bottom dead center to the top dead center. Being that said, as you can clearly see in the graph, point 2 is much higher than point 1 on both diagrams. And for process 2 to 3, the process is called isobaric heat addition process or constant pressure combustion. At a constant pressure phase, combustion occurs as the diesel fuel is injected or sprayed to the cylinder with pressurized air, which adds heat to the system. Looking at the diagram, the pressure remains constant while having a higher volume because of the fuel injected or sprayed. After adding heat to the system is process 3 to 4 or the reversible adiabatic or isentropic expansion, in which compressed and heated air expands isentropically inside the cylinder, causing the piston to move on its original position, which is the bottom dead center. Meaning, the pressure decreases as the volume increases. Also, the temperature falls while keeping the entropy constant. The last process that completes the cycle is the constant volume process that occurs at point 4 to 1. The exhaust valve remains open for some time to allow the flue gas to leave the cylinder. Let's move on to the formulas and its derivations so we can have a deeper understanding about the cycle. At point 1 to 2 is the isentropic compression process. We can say that S1 is equals to S2, or P1 V1 raised to K is equals to P2 V2 raised to K. And we know that its simplified equation is T2 over T1 is equals to V1 over V2 raised to K minus 1 equals to P2 over P1 raised to K minus 1 over K. And looking at the PV diagram at point 1 to 2, the air is compressed. So, the compression ratio is V1 over V2 or simply RK. Being that said, we can rewrite this equation to T2 over T1 is equals to RK raised to K minus 1. and P2 over P1 is equals to Rk raised to k. At point 2 to 3 is the isobaric heat addition process, which is P2 is equals to P3. So, V2 over T2 is equals to V3 over T3. The cutoff ratio is equals to V3 over V2 or simply RC. Since V2 over T2 is equals to V3 over T3, we can rewrite the cutoff ratio to T3 over T2. Once again, simply RC. Since pressure is constant, heat added or QA is equals to MCP quantity of T3 minus T2. At point 3 to 4 is the isentropic expansion process. So, S3 is equals to S4. Or, P3V3 raised to K is equals to P4V4 raised to K. Then, T3 over T4 is equals to V4 over V3 raised to K minus 1 is equals to P3 over P4 raised to K minus 1 over K. But take note that V3 is equals to V2 times RC and V4 is equals to V1. Rewriting the equation would give us T3 over T4 is equals to V4 over V3 raised to K minus 1 times V1 over V2 times RC raised to K minus 1, which is equals to RK over RC raised to K minus 1. And P3 over P4 is equals to V4 over V3 raised to K is equals to V1 over V2 times RC raised to K, or simply RK over RC raised to K. At point 4 to 1 is the isometric heat rejection process. So, V4 is equals to V1, or P4 over T4 is equals to P1 over T1. Then, heat rejection or QR is equals to MCV times quantity of T4 minus T1. Then, the net cycle work or simply work net is equals to QA minus QR. Then for cycle thermal efficiency, EC is equals to work net over QA. And as I've said earlier, work net is equals to QA minus QR. So, EC is equals to QA minus QR over QA. And simplifying this would give us 1 minus QR over QA. And we can expand this by injecting the QA and QR's formula. And that will give us EC is equals to 1 minus MCV times T4 minus T1 over MCP times T3 minus T2. But take note that T2 is equals to T1 times RK raised to K minus 1 and T3 is equals to T2 times RC. So, T3 is equals to T1 times RK raised to K minus 1 times RC. And also take note, from point 3 to 4 is T3 is equals to T4 times RK over RC raised to K minus 1. Then, let's equate both sides to T3. So, T4 times RK over RC raised to K minus 1 is equals to T1 times RK raised to K minus 1 times RC. Then, cross out similar term which is RK raised to K minus 1. And that would give us T4 is equals to T1 times RC raised to K minus 1 times RC, or simply T4 is equals to T1 times RC raised to K. To simplify this equation, let us substitute the values of T4, T3, and T2. And if you can remember, Cp is equals to K times Cv, right? So to simplify, from the equation of the cycle thermal efficiency is equals to 1 minus MCV times T4 minus T1 over MCP times T3 minus T2. Let us substitute the values of T4, T3, and T2. And that would give us EC is equals to 1 minus M times CV times quantity of T1 times RC raised to K minus T1 all over M times K times CV times quantity of T1 times RK raised to K minus 1 times RC minus T1 times RK raised to K minus 1. And simplifying it would give us EC is equals to 1 minus T1 times RC raised to K minus 1 all over K times T1 times RK raised to K minus 1 times RC minus 1. Simplifying the equation once again by crossing out similar terms, so EC is equals to 1 minus RC raised to K minus 1 all over K times RK raised to K minus 1 times RC minus 1. I mean, easy, right? Lastly, for the mean effective pressure or MEP is equals to work net over VD. And let us expound it. So, MEP is equals to work net over Vmax minus Vmin. And expounding it once again would give us MEP is equals to QA minus QR all over V1 minus V2. Now, it's time for us to input the formulas I have discussed earlier into an example problem. There are supplied 317 kJ per cycle to an ideal diesel engine, operating on 227 grams of air. Pressure 1 at 97.91 kPa, temperature 1 at 48.9 degrees Celsius. At the end of compression, P2 is equals to 3,930 kPa. Determine the following: the PVT cycle points, the expansion and compression ratio, the work net and heat rejected, the cycle thermal efficiency, and the mean effective pressure. Once again, the given are: heat added is equals to 317 kJ per cycle, mass of air is equals to 227 grams, and converting it into kilogram would give us 0.227 kilogram, pressure 1 at 97.91 kilopascal, temperature 1 at 48.9 degrees Celsius, and converting it into Kelvin would give us 321.9 Kelvin. At pressure 2 is equals to 3,930 kilopascal, the gas constant of air is equals to 0.287 kJ per kilogram Kelvin, and the K of air is 1.4. Now, let's try to solve the example problem starting at point 1 to 2. Since we have mass, P1, T1, and R of air, we can use the ideal gas law equation, or P1V1 is equals to mass times R of air times T1 to solve for V1. So, 97.91 kilopascal times V1 is equals to 0.227 kilogram times 0.287 kilojoule per kilogram Kelvin times 321.9 Kelvin. And the answer is V1 is equals to 0.2142 cubic meter. Solving for V2, we can use P1 V1 raised to K is equals to P2 V2 raised to K, since we have K, P1, V1, and P2. So, 97.91 kilopascal times 0.2142 cubic meter raised to 1.4 is equals to 3,930 kilopascal times V2 raised to 1.4. And the answer is V2 is equals to 0.0153 cubic meter. Always remember that there are many ways to solve for an unknown, and the answers should be close to one another. So go ahead and try to solve for V2 using V1 over V2 raised to k minus 1 is equals to P2 over P1 raised to k minus 1 over k. Since we have everything except for V2 of course. Let's see if we can get the same answer or a closer value. You can pause the video for a while until you get the answer. See, we got the same answer, and alternative solutions are applicable to any other thermodynamic cycles as well. Moving on, let's solve for the compression ratio. We have V1 over V2 is equals to RK, and the given are 0.2142 cubic meter over 0.0153 cubic meter is equals to RK. And the answer is RK is equals to 14. Since we already have compression ratio, we can solve for T2 using T2 over T1 is equals to RK raised to k minus 1. So, T2 over 321.9 Kelvin is equals to 14 raised to 1.4 minus 1. And the answer is T2 is equals to 925.0649 Kelvin. Moving on, let's proceed to point 2 to 3, or the constant pressure or isobaric heat addition process. Since pressure is constant, we can say that P2 is equals to P3 is equals to 3,930 kilopascal. And looking back at the given, we have QA, mass, and temperature too. For Cp of air, you can solve it using Cp, Cv, R, and K relation, which is Cp is equals to K times R over K minus 1. And the answer would be 1.0045 kilojoule per kilogram Kelvin. So let's go ahead and solve for T3. So QA is equals to mass times Cp times quantity of T3 minus T2. 317 kilojoule is equals to 0.227 kilogram times 1.0045 kilojoule per kilogram Kelvin times quantity of T3 minus 925.0649 Kelvin. And the answer would be T3 is equals to 2315.2847 Kelvin. Solving for V3, we can use V2 over T2 is equals to V3 over T3. 0.0153 cubic meter over 925.0649 Kelvin is equals to V3 over 2315.2847 Kelvin. And the answer is V3 is equals to 0.03829 cubic meter. And for RC, we can use T3 over T2 is equals to RC. So, 2315.2847 Kelvin over 925.0649 Kelvin is equals to RC. And the answer is RC is equals to 2.5028. Again, always remember that we have alternative solutions for every unknown. So go ahead and try to solve for RC using V3 over V2. Since V2 over T2 is equals to V3 over T3 once again. Pause this video if you'd like and try to solve it. At point 3 to 4 is the reversible adiabatic or isentropic expansion process. We can solve for T4 using T3 over T4 is equals to RK over RC raised to K minus 1. And let's substitute what's already given. So, 2315.2847 Kelvin over T4 is equals to 14 over 2.5028 raised to 1.4 minus 1. And the answer is T4 is equals to 1162.8499 Kelvin. And for P4 or pressure 4, we can use P3 over P4 is equals to RK over RC raised to K. Again, substitute what's already given. So, 3,930 kilopascal over P4 is equals to 14 over 2.5028 raised to 1.4. And the answer is P4 is equals to 352.8661 kilopascal. At point 4 to 1 is the constant volume or isometric heat rejection. So, V4 is equals to V1 and the value is 0.2142 cubic meter. So we can solve for QR. Solve for CV using the CP, CV, R, and K relation, which is CV is equals to R over K minus 1. And the answer would be 0.7175 kilojoule per kilogram Kelvin. So for the solution for heat rejected, we have QR is equals to MCV times T4 minus T1. So QR is equals to 0.227 kilogram times 0.7175 kilojoule per kilogram Kelvin times quantity of 1162.8499 Kelvin minus 321.9 Kelvin. And the answer would be QR is equals to 136.9676 kilojoule. Since we got all the PVT cycle points, we can solve now for net cycle work or simply work net. So, work net is equals to QA minus QR. Work net is equals to 317 kilojoule minus 136.9676 kilojoule. And the answer would be 180.0324 kilojoule. Moving on, let's now solve for the cycle thermal efficiency. We can solve for cycle thermal efficiency using EC is equals to work net over QA, or EC is equals to 1 minus QR over QA. Let's solve it together and I will use the latter one. Let's see if we can get still the same answer. Once again, you will use EC is equals to work net over QA. So for my solution, I have EC is equals to 1 minus 136.9676 kilojoule over 317 kilojoule. And the answer should be 0.5679 or 56.79%. And I think we got the same answer, right? Lastly, let's solve for mean effective pressure or simply MEP. MEP is equals to work net over VD, and expounding it would give us work net is equals to Vmax minus Vmin. And you know already the value of Vmax and Vmin, right? So, MEP is equals to 180.0324 kilojoule over 0.2142 cubic meter minus 0.0153 cubic meter. And the answer is 905.1403 kilopascal. There you go! We got all the answers that we need. And oh, before I forget, we can check through the PV and TS diagrams if our PVT cycle points are correct. Let's take a look at the diagram. This is a faster way to check if you are in doubt about your answers. But don't rely on this method. This is just for checking, okay? As you can see, P1 is the lowest pressure and P2 or P3 being the highest. So let's check if the result we had agrees with the diagram. We have pressure 1 is equals to 97.91 kilopascal being the lowest, followed by P4 is equals to 352.8661 kilopascal, and P2 is equals to P3 at 3,930 kilopascal being the highest. Go ahead and check for volume and temperature yourself, because I'm too lazy, okay? Here's an example problem so you can practice on your own, and the answers are provided as well. So that's it for today's discussion. I hope you learned something new. Don't forget to like this video and subscribe. Thank you for watching!